Open the record and open the share screen. Okay, so Junyi, you can start anytime.
Okay. Okay. Hello everyone. I'm Jing Duan. Today is my paper reading, and the title of my paper is Augmented Reality Visualization, a review of civil infrastructure system applications. First, I will review the abstract of my paper. Um, the main and the main points of abstract is the big difference between an AR and other visualization technologies are three aspects. First is it reinforces the connections between people and abstracts and promotes engineers' appreciation about their work context. The second is it allows engineers to perform field tasks with the awareness of both physical and the synthetical environments. And third, it offsets the significant cost of 3D model engineering by including the real-world background. And this paper reviews critical problems in AR and investigates technical approaches to address the fundamental challenges that prevent the technology from being usefully deployed in CIS, civil infrastructure system applications. Firstly, I want to ask a question. What are the differences between VR and AR?
Maybe VR is creating like a whole virtual environment, and AR just magnifies an information into a real world.
Yes, that's good. That's you said majority of the differences between VR and AR. Yes, that's correct. In contrast to VR, AR preserves the user's awareness of the real environment by compositing the real world and the virtual context in a mixed 3D place. And just as Remy said, for this purpose, AR must not only maintain a correct and consistent spatial relation between the virtual and the real objects, but also sustain the illusion that they coexist in the augmented space. The second is the awareness of the real environment in AR and the information conveyed by the virtual objects provide users with hints to discover their surroundings and help them perform real-world tasks. And finally, and the most important is AR offers a promising alternative to the model engineering challenge inherent in VR, but only including entities that capture the essence of the study. These essential entities usually exist in a complex and dynamic context that is necessary to the model, but costly to replicate in VR. However, reconstructing the context is really a problem in AR, where modelers can take full advantage of the real context, for example, terrains and existing structures, and render them as background, thereby saving a considerably amount of efforts and resources. Okay, and then the paper talks about AR in agricultural, engineering, and construction, which also called AEC. And the first two applications are visual collision avoidance and reconnaissance of damaged building. I will talk more about these two applications later. So let's go to a next slide first. this is a picture of visualization of construction processes. Research was conducted to enable the visualization of construction operation in outdoor AR to facilitate the verification and validation of the results of simulated construction processes, with minimum effort spent on creating 3D models of the surrounding environment. And then finally is the collaborative AR visualization. The tabletop collaborative AR visualization helps to bridge the gap between paper-based static information and computer-based graphic models. It reflects the dynamic nature of a job site and preserves the convenience of face-to-face collaboration. Then paper talks about two challenges associated with AR. And the first is spatial alignment of real and virtual entities, which is also called registration. The goal of spatial registration in AR is to properly align real-world objects and superimpose virtual objects with respect to each other. Without proper registration, the illusion that two worlds coexist inside the augmented space will be compromised. And we'll let's talk about the registration first. The following is the registration process. And the first is viewing by positioning the viewing volume of users' eyes in the world coordinate system. And second, positioning virtual objects in the world coordinate system. Third, determine the shape of viewing volume. And finally, converting virtual objects from the world coordinate system to the eye coordinate system. The methodology behind the registration is based on mathematics, matrix calculating. And the next challenge is visual illusion of virtual and real-world coexistence, also called occlusion. In an ideal AR visualization, real and virtual objects must be seamlessly blended in all three dimensions. The result of composing an AR scene without considering the relative depths of the real and virtual objects is that the graphical entities in a scene appear to float over the real background rather than blend or coexist with real objects in that scene. This phenomenon is commonly referred to as incorrect occlusion. This picture shows what is incorrect occlusion. You can see like this one, it seems a man in front of a truck, but if there's a incorrect occlusion photo, that seems so weird. So how do we deal with incorrect occlusion? The equipments and technical is a real-time time of flight TOF camera, RGB video camera, OpenGL shading language, render to texture techniques. By all of above equipments and technique, we can correctly solve the depths of real and virtual objects in real-time AR visualizations. And in order to realize collision, we have a very important step named two-stage rendering, which is a depth buffer and color buffer. So what is depth buffering? Also known as Z-buffering, and is the solution of a solution for hiding surface illumination in OpenGL, and it's usually done efficiently in the graphics processing unit GPU. So what is the methodology behind it? Is like for an incoming fragment as a certain pixel, the fragment will not be drawn unless its corresponding depth value is smaller than the previous one. If it is drawn, then the corresponding depth value in the depth buffer is replaced by the smaller one. In this way, after the entire thing has been joined, only those fragments that was not obscured by any others remain visibly. So by this, we can deal with incorrect occlusion. And finally, this paper introduced three implemented ASD applications. The first application is augmented reality assistant and building damage reconnaissance. As before, following a major seismic event, rapid and accurate evaluation of a building condition is essentially for determining its structural integrity for future occupancy. The inspectors should designate affected buildings as green, yellow, or red for immediate occupancy. However, this approach is slow and often too subjective, which may suffer from misinterpretation. Now, by AR, we have a new algorithm called LSD, line segment detector, for automating edge extraction. The picture shows how it works. The picture shows the dynamic overview of measuring earthquake-induced damage manifested as a detectable drift in a building's facade. And the previously stored building information is retrieved and superimposed as a baseline wireframe image on the real building structure after damage. The sustained damage can be then evaluated by comparing the key differences between the augmented baseline and actual drifting building edge. And this picture shows how it works, and not only for seismic evaluation, for normal evaluation, we can also use this augmented reality to assist in building damage reconnaissance. For example, this is the vertical baseline of the building structure.
Yeah.
Is also qualitative alternative for visual inspection of the local damage. By observing the graphical discrepancy between the vertical baseline and the real building edge, the on-site reconnaissance team can approximately but quickly assess how severe the local damage is in the neighborhood of the visual field. In other words, the larger the graphic discrepancy, the more severe the damage. And the next application is augmented reality for geo-referenced visualization of buried utilities. The background of this is the underground infrastructure in US comprise of about 20 million miles of water and wastewater pipes, conduits, and cables. In some locations, and since neither the machines nor their skilled operators can see what lies buried in their vicinity, utilities are frequently struck and damaged. So researchers try to use augmented reality to solve this kind of problem. This picture shows a cabin-mounted display on persistent AR visualization. And by this camera, the truck driver can see what kind of pipelines are under the soil. So they can dig very carefully and try to avoid this pipeline to have a safe construction. And finally, the final one application is augmented reality for collaborative design and information delivery. According to a survey in construction and civil engineering, research shows that a large percentage of students fail to properly link their classroom learning to real-world engineering tasks and the dynamics and complexities involved in a typical construction project. In addition, Several academic surveys have indicated that students complain about the limited use of emerging technologies and advanced problem-solving tools in classroom. Luckily, one of the fastest emerging technologies in collaborative energy education, training, and design is visualization. And these two series of pictures shows the AR used in education area. The motivation behind is to allow multiple users to observe the animation from different perspectives and remotely shift the focus of the shared working place in a natural approach. And the series of photos at the bottom is still erection activities at different timestamps. The focus of the shared workspace can not only be switched spatially, but also temporally. Users can choose to observe the animation at different speeds or jump instantaneously along the timeline. Okay, thank you. This is my paper review.
All right, thank you. Any question from the class? So I have a quick question, Junyi. Why this paper uses GPS?
I'm sorry, GPS used in I see GPS.
Yeah, so
okay,
in the yeah in
I got it. And in GPS in a registration process, a spatial alignment of real and virtual entities.
So their applications are mainly concentrated on outdoor applications, right? Because GPS, we know GPS is not functioning
Yes.
Indoor. Okay. One thing that about AR is, the most difficult part about AR is the anchoring problem. Like you do have the real world objects and you have the virtual objects. You want to anchor the virtual objects on top of the real world objects. That requires a lot of localization, requires a lot of computation. So it's still the most challenging part of AR. I think this study has this kind of shortcut solution that they uses the GPS to localize themselves and to speed up the anchoring process. But most of the AR application today, for example, if you're talking about HoloLens, they rely on computer vision. So it's kind of like they have the depth camera to recognize the environment, which we call environmental understanding. And by adjusting, running machine learning to check the overlay portion, they somehow infer how you move. Of course, they also add IMU and other accelerometer, try to recover how you move in the space. If you move to a different room and then come back, usually you will see everything's shifting a little bit. It's all because of the anchoring issues. So that's one comment I want to make. So this paper does have a very specific application area. It's mainly for outdoor, for structural inspection, like you mentioned, right? So
but in paper.
Yeah, so maybe that's why maybe they developed this kind of GPS system. I think by checking the figure, I didn't read the paper, but by checking the paper you shared, I think the majority of the system are actually about that, receiving the high accuracy GPS data and to synchronize the rendering of that. Yeah, so
Yes,
that's just
but in this paper, in the registration process, the professor and in the registration process, the paper put forwarded that and to use the world coordinate system. But I think that's not only use the GPS because in paper it says because there are virtual objects and the paper itself, we have in total 6 degrees of freedom. I think by they detect this degrees to solve this degrees of freedom, they not only use the GPS because it's mostly based on mathematics and determine the degrees we have.
okay. Any more questions or comments from the class? If no, I shared the link in the chat box. Please use the link to evaluate Junyi, and that will also conclude our paper reviews. All right, give you a second to do that now. All right, guys, so let's continue our data analytics part. Let me share the screen first. First, let's just, it's been a while, I know. And so let's just review the machine learning algorithms we covered earlier. So if you recall, we talk about the, machine learning is not just one algorithm, it's actually a school of multiple algorithms. And depending on the logic, depending on the mathematics they are using, we have different classes of machine learning methods. Some are older, some are newer. So we do have something from the traditional statistical science, such as the Bayesian method. You guys remember we talk about the Bayesian belief tree. Like if you have the conditional, if you do have some prior knowledge about the conditional probability, and so you can basically form a network of that. So by having one observation, it's kind of like you are spreading that reasoning process, so you can calculate the likelihood of a certain event. So that's called the Bayesian belief network, or BBN. In that way, we can do a fast diagnosis, right? So if a patient comes to your office, you just by asking them simple question or make very simple observations, then you can basically get the estimate for a certain disease, right? And also, this is also the approach that Microsoft is using. If you are running issues with your Excel, with your Word, you just by answering a sequence of questions, then Autodesk, Microsoft will infer what could be the problems you are facing and what could be the solution, right? And this is also very similar decision tree. Once again, this is pretty old. And also have a newer method, especially the neural network based method. And remember, neural network is the way to simulate how human brain or any brain works, right? So this is a feedback system that you have the arrow from your prediction, and we run the back propagation to correct the threshold, to correct the add-in, and depending on how many layers you have, we call them traditional neural network or the deep neural network, or which we call today deep learning, right? And also regression, that is you have the observations and you're trying to feed some kind of a formula to describe the tendency of your methods of your data. That's in general this kind of this group of methods called regression method, and depending on the formula you are using, we do have like logistic regression, linear, nonlinear models, and depending on how you run the learning process of the regression, we have the stepwise regression. Stepwise is kind of like we add one X into the formula and then we try the model. If we are not happy, we run another, we add another X in the formula. So we keep doing that. That's called stepwise. We also talk about clustering and classification. So the difference between clustering and classification is for clustering, we don't give any label to data. So we just threw all the data to the machine learning model, and the machine learning model have to somehow tell how the data looks like, what the structure of the data look like, the pattern of data looks like, and try to group them, right? But the classification is kind of like we tell them, hey, if you see this kind of data, it's green bean. If you see that kind of data, that's red beans. If you see, this kind of data, that's apple. Then we teach them certain data, and now we give them new data, ask them to classify them in the right group. That's called a classification. And depending on that, we also talk about the important concepts in machine learning, parametric versus non-parametric, right? So parametric is more of we assume a function and we try to fit the values for the parameters. Non-parametric is we don't assume any function, so it's a black box. It's a box with some kind of structure, with some kind of a feedback structure, but we don't assume any of the parameters or functions. It learns by itself, so this is a black box. supervised over unsupervised. Supervised is more kind of like, hey, if you see this kind of data, it's an apple. If you see that kind of data, it's a banana. Unsupervised is I don't tell you what they are, but I try to group them based on the similarity in their pattern. That's supervised and unsupervised. And also we talk about the dimensionality. Remember, I mentioned that there's a phenomenon called the curse of dimensionality. Whenever you are increasing the dimension of your problem, such as y equals f, x1, x2, x3, you keep adding x into your model. At the very beginning, the prediction performance will improve, but after a while, you will start to see a sudden drop of the performance. It's all because when we are moving from a low dimensional problem space to a high dimensional problem space, everything will become so strange. Remember that? Like the number of data points you need to train your model will increase exponentially, and also the data will spread to the corners. It's very difficult for you to find representative data from your sample process, right? So the first step of all modern machine learning approach is actually dimensionality reduction, or which we call feature extraction. You guys remember that? Like how we can find out the right features. And so with that, we talk about the important, newer methods. For example, one method is called a convolutional neural network. You guys remember that? It's kind of like I threw you a picture and ask you to predict what's in this picture. It's a cat or dog. But if this is 1K picture, which means it has more than 1 million pixels. So if we use the raw pixel number, each pixel, you guys remember that? If it's a grayscale picture, each pixel can be converted into a number between 0 and 255. So if we use the raw pixels, we are talking about 1 million inputs into a neural network. That would be too much. So convolutional neural network is nothing but running some kind of matrix calculation. So we treat the original picture as a matrix, and then we have another conversion matrix. We just multiply both. That's multiplication, right? And then we got the newer one. The newer one will be smaller in size, but somehow we figure out how to run the multiplication to reserve the most significant features. You guys remember that? So we do it multiple times until the input becomes around 30 to 40 inputs. So we are running from 1 million potential inputs to only about 40, 50 inputs. That process is called a feature extraction. The reason we call this is a method, very popular method today in computer vision image processing called convolutional neural network, or CNN. The reason we call it convolutional, it's because we want to reduce the dimensionality of extracted feature. You guys remember that? And also another example for feature extraction is this, sparse coding. Yes, also remember this, right? So we have a bunch of pictures and we cut the pictures into pieces, right? And we can identify 64 such pieces, and we can reproduce anything in our universe with those 64 pieces. That's why we call the 64 pieces as the super complete basis, right? It's kind of like a magic, right? So it means that I got some pieces from like a dog pictures, but I can reproduce pictures of cars. I can reproduce pictures of human faces. I can reproduce pictures of chairs. But the thing is, if you check the super complete basis, they are representing lines of different degree. And surprisingly, remember that bioscientists who study the mammal visual neurons, they also discover similar thing. Certain degree of lines will activate certain areas of brain cells, and a higher level brain cell is just checking how much of this 45-degree line brain cells are activated, how much of the 180-degree brain cells are activated. So it becomes a high-level judge that just check the distribution of the activation and then link it to the knowledge. So we know, oh, this is a cat, this is a dog. You guys remember this one? So think about this way. This is actually a feature extraction or dimensionality reduction, because our machine learning model cannot process complex information, raw information like this. So what we are doing is just to check the percentage for each of the super complete base elements, like 0.2 of this one plus 0.3 of that one. So we only focus on the 0.2 and the 0.3 number. Technically speaking, that is a dimensionality reduction. And coincidentally, this is also how our brain process the rich information in the world. Think about the amount of information our brain has to process, right? That's huge amount. And so because of evolution, our brain actually developed this function to reduce the dimensionality, extract the features from the visions, and then only focus on the high level abstraction or high level combination of the components. In that way, we recognize, oh, this is Rahid, this is Rami, right? So that's also a very important concept for machine learning algorithms. Let me just go back here. Okay, and also we talk about the Bayesian, right? So the Bayesian is basically conditional probability, that this is actually reflects the reasoning process. If this thing happens and the likelihood that thing will happen is this much. And then I keep doing that until I got the likelihood for different options. So I know what is the most likely. This is the Bayesian method. And the one thing we didn't talk about is the reinforcement or reinforced learning. So let's talk about that first. Let me open. Let me open a slide quickly. I'm going to use old presentation I gave at Zachary. So that one with notice. That one covers a very interesting application of reinforcement learning. So we will see what that means. Okay. You guys can see the slide here. Okay, so I was giving this presentation at Zachary during an event called Rocks. So they invite people from different departments Friday morning at 7:30 to share some interesting stories or interesting works they are doing. And the CEO of Zachary, John Zachary, often sit there. So this is actually the first Rocks presentation I gave. And after that, I got invited every time. So this is the site layout using genetic science. Let me just share what the problem we are facing. Okay, so job site layout, facility locations. This is a drawing of a power plant project. Okay, you probably cannot tell the size of this, but let me show you. I don't know. This is something called a cooling tower. The big fans. You can imagine this is kind of like 3-story buildings with some really big fans rotating to get steam. To cool down the entire power plant structure. And those are combustion turbines and the generators to generate, the power. We call each one a rack. So it's a combustion turbine connected to a generator. The combustion turbine burns the gas or coals. And so basically start to generate the mechanical power. That will drag the rotation of the generator, so we generate the power. Makes sense? So the size of this site is about 8 acres, so it's pretty big. Usually a big challenge to a lot of project manager is where to put, let's say, material storage, office building, lunch trailers, tool rooms. The tool rooms is also very important. The concerned workers will have to travel to the tool rooms to get all the tools they need on a regular basis. So most of the project managers just randomly pick places. So they got the pencil, they got this site drawing. They just say, hey, I want to put my office here, so it's closer to the entries. I want to put the storage there, so it's closer to the, to the work area. So what's the potential problem here, guys? The potential problem is we don't know if this particular layout of different trailers and facilities can reduce the travel distance. You got my point? So imagine for 8-acre job site, if you are a construction worker and you are working, let's say in this area right now, but the tool room is at another corner, then how long I have to walk there to get the tool and come back? A lot of people tend to overlook that, tend to ignore that because it is what it is. But if you do a quick math, you will be surprised at how much time people are wasting in just traveling and walking on a job site. So mathematically speaking, there must be some optimized layout to show, where we should put different things. Okay, so this is what I did exactly. I think the best tool for us to use is Excel. People understand Excel, right? So first I import this drawing into Excel. And as you can see, I basically changed the columns and rows as squares. So each square represent 100 feet by 100 feet space. Okay, so that is the granularity I have. And then if I put the office in certain area, then I know it's probably, let's say, number 5 and 80. So I can identify the location of that. And if you say the tool room can be D10, so that's how we identify that. And then, this is how it looks like, right? So we can convert them into numbers. So let's say 1, 2, 3, 4, 5, 6, 7. That represents different facility, like tool room, office, storage, and also different work areas. And all the green, I use the number 0 to show their available lots, which means, I could possibly move this tool room to any of the zeros. Make sense? So this is a step we convert a spatial problem into a pure mathematical problem. And then here's the magic. If you get the first line up, and then for the second line up, you just basically put the head to the tail. So basically, you can convert the entire job site, the 2D, into a 1D data array. Make sense? Because they are numbers, right? So let's say if it's kind of like this, then your number would be 0, 0, 0, 0, 0, 0, all the way to here, and it's in 1, 2, 3, and 0, 0, 0. That is how the long array look like. But if I move 1 to somewhere here, then the new array would look like 0, 0, 1, 0, 0, 0, 0, right? So when you are changing the layout, you are just changing what? This data array. And so I developed a formula inside Excel to calculate the travel distance based on this array. It's a mathematical problem, right? So let's say I know the frequency that people need to travel between 1 and 5. And I know each square represents what? 100 feet times 100 feet, right? So then mathematically, I can calculate how long from 1 to 5. And I also know the frequency. So there's a way to generate this total travel distance based on array that representing certain type of layout. Make sense? And whenever you are changing the layout, you are changing nothing but just the array, and which represents a new travel distance. Make sense? Okay, so the concept is we just try different kind of arrays, different kind of layouts, right? Until we can find a lower number of travel distance. So, okay, so now you know the frame of the problem. Okay, so here is the killer. All possible solutions for this particular job site. It's kind of like we have this many cells. It doesn't look like too much. Here's the thing, it doesn't look like too much. But let me show you. If we want to run over all the possible combinations or all the possible arrays, the total number for this project is more than 160 million. And we are talking about the minimum travel distance, the one array that is showing the minimum travel distance. The chance is smaller than winning the mega millions, the lottery. Of course, we are not lucky. I have never seen anybody, I don't know anybody who have ever, won this mega million, okay? So if we run it, let's say with my computer, let's scan over all the possible combinations, all the possible arrays, that would take my computer 3,360 days. That's around 80 years. You guys understand that the complexity of the problem, of the spatial optimization problem, right? Since for this particular layout, you could possibly just move this little, facilities 1 square away. That's one combination. Now imagine the possible locations for them. And this is a combination problem, right? You could just move 1, or you could move 1 and 2, or you could move 1 and 2 and 3, and you could have different sequence of moving them. So anyway, by doing the math, this is the chance and this is the cost to run all the possible combinations. Now, this is when where the reinforcement or reinforcement learning machine, that's a major part of a machine learning approach can take place, can help. Okay, so I'm going to introduce the most popular reinforced machine learning, genetic algorithm. And I'm going to show you how machine learning can figure out a trend, a pattern that can significantly reduce the time for you to find the optimal layout, okay? And talking about genetic algorithm, I have to talk about genes. You guys know genes, right? So each cell has a gene. All the creature in the world, we have these genes. And so genes is actually the segments of DNA, and we know the DNA is part of a chromosome. So this is a human cell, and this is the core, the nucleus of human cell. If you go deeper, we see this kind of X or Y shape of structure. We call them a chromosome. The chromosome is actually a folded structure, the look of folded structure of DNA, right? So DNA, they fold them up and it look like this shape. That's called DNA. And the genes is actually the elements of DNA showing the combination, of I think it's 4 kind of nucleotides, right? And by combining them different ways, we can develop different proteins. We can develop a different component structure. Okay, so what is evolution? Why creatures are becoming different, and why we are evolving, why we are developing better functions. This process is called evolution. So here's the thing. Imagine we have a male and a female, and the female and the male each will contribute half of their genes. Make sense? So they come together. This is called, they contribute half of them. This process is called a crossover. And so they combine, and then this is a new type of gene. So ideally speaking, it carries 50% features from the mom and the 50% features from the dad. But we also have a mutation. We know the children would look like their parents, but still a little bit different. So probably about 1%, 5% mutation will happen, which means certain genes will just randomly change. And because we are carrying the features without the mutation, so we are improving a little bit. So we are testing, right? So how do we, evolve mathematically? This is how it looks like. Let's imagine we have 100 people, and each person has this kind of gene to represent their, features and everything. Only the best people can attract best people. This is common sense. Makes sense? So if you're a lady, you try to find a partner for your life, you always find the one you like the most, or whatever male that carry the genes that you like, that you perceive to be better. So here's the rule. Actually, it doesn't only apply to human beings. It's applied to any kind of a creature. The best people only attract the best people. So they get married, right? And each one will cut their gene into half. Let's say called crossover, and contribute half of their genes. And this is called what? It's kind of like they are sharing their genes. So we have this child. And then of course there will be some mutation. Let's say in this time, 11% of the genes will be a little bit different, will be randomized. So let's say the mutation rate is 0.11. Make sense? Guys, what happened? This is magic. This kid will go back to the pool to replace the voice. You got my point? So this is actually the survival of the fittest. Imagine we still have this 100 people or 100 genes here, and the two best that get married, get a birth, have a new child. This child will come back to the pool and replace the voice. Now, think about that. If we keep doing that, what would happen? Only the desired genes will survive. Make sense? Only the preferred genes will survive, because the voice is often replaced by the best. Okay, Maybe this doesn't sound politically correct, but this is what's happening, okay? Now, imagine those genes, what do they look like? They look like this, right? You know, we convert that 2D drawing into a long array, and that long array just look like gene, and each gene represents a number. The number is what? The total travel distance. Now, what is a better child? The one that represents what? A lower travel distance. Make sense? And imagine we randomly generate 100 arrays, which means I just randomly pick 100 layouts from, you know, this many of possible combinations. And I start that kind of artificial evolution. You know, the two best get married, share half of their genes, have some mutation, come back, replace the voice, which is the array showing the longest travel distance. And we keep doing that, and by the end, it should be better than the original 100 randomized arrays. Make sense? So this process is called reinforced learning. Why we call it reinforced learning? Because we somehow, this process of the best kid going back to the pool to replace the voice is to reinforce the good features. Make sense? So evolution or survival of the fittest is a kind of reinforcement to strengthen the best, the good features, and to weaken the wrong features, the bad features. Make sense? So that's why I call it reinforcement learning. And in this particular case, because of the mathematical basis, is based on how evolution happens. So we call this genetic algorithm. All right. So let's see this example. Instead of running all the possible combinations, the 160 million combinations for 8 years, if we run this kind of genetic algorithm, you know, we run 100 arrays randomly for the first round, we do this kind of marriage, we give birth of this child, and it comes back, replace the voice. We have a new generation of 100 people, and we keep doing that. After one, you know, this is how we do it, you know. So basically, I name facilities 1 through 7, and I also gave this frequency matrix, which means from facility 1 to 7, people tend to travel 24 times a day. From, you know, 2 to 7, 0 times a day. And from facility 1 to facility 3, people on average travel 10 times a day. So this one shows the importance of, you know, the two facilities. And also we can give data like the walking speed, the salary rate of the construction worker, the crew size, the work hours, how many hours per day, and also crew size. So we give all the information so we can get a better calculation of the walk distance. And then we start to run this genetic algorithm. And this one shows what? This one shows number of simulation or number of generation. So it's kind of like this is the parent, this is the child. So that's called one generation. From parent to child, that's called one generation. And this one shows the best travel distance. Now you can see just after about 100 or maybe less than that, 78 generations, the total travel distance reduced from 55,000 feet to about just 51,000 feet. You can see that? So now we can see this is the process that good genes got passed over to the next generation, bad genes got replaced. So we start to, what do we call convergence? We start to converge into a better combination. And you know, this is at the original layout. This is after 1,000 trials, the recommended layout. As you can see, they basically just say the two facilities should come here and the one should come here. For some reason, it might be because a lot of works will be done in this area, so people tend to travel to 1 and 2 more often. So let's put them closer to 6 and 7. Make sense? So any improvement? So before running this genetic algorithm optimization, based on the original layout proposed by the project manager, for one crew, the daily travel distance is actually 55,000 feet. Now, after running that optimization, it was reduced to 19,000 feet. 78 hours wasted on walking traveling on job site can be reduced to just 2.8 hours. So that translates to about $1 million. I run another project. It's not this one. It's a solar panel project. The solar panel project, it's a big farm, an even bigger yard because you have to put a lot of solar panels, right? And you also have the kind of like a golf cars to move the materials around. So for that project, we did the estimate just by moving around the facilities, we could potentially save $1 million waste on traveling. Okay, so how long does it take? I basically also did the calculation. It only took about 26 minutes to find out the optimal layout. What is the original number if we scan over all the possible combinations? 8 years. So now you guys can feel how reinforcement learning, by reinforcing good behaviors, by punishing bad behaviors, reinforcing good features, punishing bad features. Punishing bad features in this case in genetic algorithm means they don't have a chance to get married, to pass over their genes, right? We can reduce the computation time from 8 years to only half hour. So is it just mathematics? No. What's this? That's the Japanese Shinkansen, right? So this is the high-speed rail in Japan. And you probably notice that the nose is mechanical engineering that by designing shape the nose to reduce the friction. Did any engineer design this? No. If you check the specification, they run genetic algorithm. So you can imagine they quantify the shape in numbers. Let's say the length is a number, the width is a number, the curve is a number. So you have certain numbers. And then numbers connecting together is what? It's an array, right? And the array looks like a gene. They randomize, let's say 100, 200, 500 such numbers. They run this genetic algorithm and the magic happens. So imagine we simulate evolution. And for each evolution, for each generation, we have different kinds of designs until the best designs start to emerge from there. So what is the benefits? Energy consumption reduced from, this is a series 1, series 0 high-speed train to this N700, reduced by almost 50%. So we reduce half of the energy use just by changing the shape of the nose. And this one was not designed by any human being, but just by this reinforcement learning. And this is a German steel manufacturer. And for steel manufacturer, they have a very busy schedule. The time of the unit of time for their schedule is actually minutes, like from 7:05 a.m. to 7:10 a.m. you should do this, and from 7:11 to 7:14 you should do this. So their schedule is very busy. Now it becomes a big problem how to optimize their schedule, how to optimize their sequence, because there's so many activities happening in such short period of time. It's beyond the capacity of human being to do anything. Make sense? So in this way, they run genetic algorithm once again. So their, what do we call the fitness function, or the outcome is what? The duration. So the duration should be minimized. So they run this evolution until they figure out certain kind of schedule that can give you the minimum duration. So that's reinforcement learning. And let me show you this. So this is actually the tool that I developed. And as you can see, you got this facility, and of course, the calculations is done backend that I do have the matrix that how to calculate that. So without this simulation optimization, oh, you guys can see my screen or not? Okay. You guys can see it now? Okay, so like I said, this is the tool, this is Excel. I converted the drawing into these numbers already. So these are just numbers, right? It's just regular Excel, and without any optimization, this can also become a very handy tool for people to think about their facilities. So for example, now the total travel distance is 59,000 feet, right? So let's say if I just want to change to 0 and move 1 here, you just do this number change. And now this becomes 57,900 feet. Let's say I just want to change to 0 and move it 1 here. This one changes to 72,000. You guys got the point? So every time you change the number, you change the array, and I did this calculation. So basically you change the number. Make sense? Now, it take me like I mentioned, 8 years to try out all the possible combinations. Now let's run this genetic algorithm. So first I want to define, my goal is to minimize something. Minimize what? I say this number. If you go this number, it shows, this number, right? So BF15, I want to minimize this number. By doing what? So basically I say by here, it's called order. So now if I connect all the numbers, it becomes what? A long array, right? And the long array has all the numbers. I don't want to have repeated numbers. Let's say I don't have 2 ones or 3 ones. So the method I use is actually change the sequence. It's kind of like you have all the boxes, you just want to move them around. You change the orders of them, change the sequence of them. So basically what I'm telling this genetic algorithm program is I want to minimize this number by shuffling the order of this array. Make sense? So this one actually the long array defined by this Excel spreadsheet, shuffling the order until we can minimize this one. All right. And then let's see sighting. How many trails I want to run? By default, it's 1,000 trails. All right. Here, that's 20,000 trails. And also you can define different things like what kind of random seed you need, which means what kind of first generation you want. You can define the first generation based on experience to further shorten the optimization time or whatever, just randomize. So I say just randomize, okay? And I say every trail just to show you how it looks like. Okay, so everything's good. It's very simple, right? This is added in Excel. And just so start. Do you guys see that my Excel is flashing? The 1, 3 that are changing, what happens? My genetic algorithm is doing this automated trying. And let's see, this is the progress it's making. The starting point is around 60,000. Now by trying, they know, oh, by doing this, I can reduce it to 40,000. Then they figure out this is the feature I should follow. This is the gene I should follow. This is the guy should have more marriage. And so they just basically stick to it. They keep passing over that good feature. You can see it never comes back. Makes sense? Because the voice, the kid, always got replaced. So this curve never come back. It just keep dropping. Now it's what? That's ridiculous. It's already 20,000. See? And we, of course, we can let it run forever. If I reduce the animation, it will be faster. So let me pause it a little bit and see if we can. Okay, let's rewind. It also tells you now the trail 228 is the best, but of course, it's already 460, which means what? From this generation to this generation, we have never got a better person, right? We know that, it's kind of like human history. We always got the smart people, right? But we have to wait for 200 years, every 200 years to have a smart people, a smart person could change the history. Same thing here. You can never expect this good gene happen all the time. Why? Mutation. The mutation is the random factor in this reinforced learning. We are trying different ways, trying different solutions until we are lucky to find this certain mutation that lead to better genes, and we bypass that gene. We preserve that very carefully and bypass that. Okay, so until now, almost 1,000 trails, but still the best kid was from the generation 228. We still haven't seen any better kid, right? And you see that's why the lines is going this way. Now, see, we got to improve. So it's 85, right? 852. And this one shows the log of that. So it's trying. So let me pause here. You guys now have a sense of genetic algorithm, how it works, right? So this is actually very straightforward thought of using bioscience, okay, and to inspire that. Now think about what else we can do with this reinforced learning. Let's say, I don't know, let's say you have different designs for a building, for a structure. You want to find out the best use of reinforced concrete. You don't know about the size of the concrete, the rebars of the concrete, the numbers of that. You can definitely run genetic algorithm to give you the best design, structure design. Or you want to design a structure that can sustain the hurricane the best and can give you the most space. You can parameterize the design of the building, like the head of the building, the level of stories, the facade of the building, and give it to the genetic algorithm. You guys can search YouTube on YouTube, search genetic algorithm building design. I guarantee you will see a lot of interesting work that the people using genetic algorithm to optimize, to automate the design something. Let me search it quickly and hopefully we can find something. Here we are. Let me share my screen. You can see this one, right? So this is the design optimization using genetic algorithm. And once again, architecture. And this one is to optimize the energy solution. We know this is called a window to wall ratio. In order to get a better, natural light to replace the use of artificial light, the windows must be bigger. But the bigger windows in hot area will increase the use of AC, right? So we do have to find a balance of that. So this is the shape. Let me see what it looks like.
To look at an example of design optimization using.
This is Grasshopper. It's a tool to run genetic algorithm for this design.
Component that's falling on that surface. Blue being the lowest radiation and yellow being the highest radiation. Okay, the options, I don't mess around. Okay, well, first work on.
Once again, the outcome we call this fitness function. Basically shows that what we desire, and here is to minimize something. So probably minimize the use of material.
Minimizing the thermal radiation.
See, it's changing and testing.
It's going to take a long time because the analysis take a long time, and because we have a number of parameters, the 4 parameters, I think, 50 the mass, okay, and this one apparently has a lot of blue faces.
So even you cannot get the optimal solution, but still, you get a much better solution in your original design, and it can also be like a urban planning, like this one. The only thing they are changing is the XY of this building to see how it will minimize the in fact impacts on other buildings. That's also genetic algorithm, right? I don't know if we have better. Yeah, remember there's a good case study. I cannot find it now. Is that this one? Yeah, let me stop here. I think you guys get the sense how reinforcement learning looks like. So fortunately, we covered, all the, I think the key concepts of machine learning, and hopefully this gives you a good overview of how machine learning looks like, and hopefully machine learning is not a black box to you guys anymore. It's just a bunch of mathematical, it's just a bunch of logic, reinforced neural network to simulate. I think, machine learning is actually the way we simulate nature. Neural network simulates how brain works. Sparse coding simulates how our brain sees world and abstract information. Reinforcement learning simulates evolution, right? So it's nothing. It's actually just the bell-inspired approach. But there's another important concept I need to cover today. It's a little bit abstract, so bear with me. And I guarantee you guys, you will see this question in the final exam, okay? So remember when we talk about regression analysis, there's a indicator to show how good the prediction is, how good the model is. It's called R-square. You guys still remember that, right? Oh, let me share my screen. You guys still remember that we have this R-square to show how good your regression model is, right? So this R-square basically compares with the voiced prediction model, and we convert it into a number to 0 to 1. Is R-square the only way to evaluate the performance of model? No. Actually, nowadays, we have very important methods to evaluate the goodness of a machine learning model. That's called a model evaluation. So that's the last concept I want to cover with the machine learning, model performance evaluation. So it's the first thing I want to cover is something called confusion matrix. So what is confusion matrix? Okay, so bear with me. This is a very important concept. So let's say we have 2 dimensions. One dimension here is the actual. So that's the fact. That's what actually happened. And the dimension here is the prediction. So it's actually what I predicted. Okay. So for example, let me give you an example. A person is actually infected by COVID-19. That is what? That is fact. So that comes here. And then I use this test to predict if this person is infected or not. Can I always give you the right answer? No. Nothing is perfect. Makes sense? We always hear from the news that this person got infected, but the test returned as negative. Or this person doesn't get infected, but test returned as positive. So you probably have heard of the word called false positive or false negative or true positive, those kind of things. This is what happened. When this person got infected, actually infected, and the test returned as positive, so the predicted, which area we fall in. So let me show you this. True, false. That one shows if this person is affected or not. Positive, negative, that is the test result. Makes sense? So if this person actually got, let me still play that, actually got infected, so that's the fact, right? And then I predict that this person got infected. This is called true positive here. Makes sense? So here is true positive. It falls here. Make sense? All right. Another situation can be this person is not infected, but our test is wrong and return. Also, this person is not infected and our test is correct. Return negative. So which area should I highlight? Which area it belongs to? Anybody?
False negative.
No, because this is still correct. So it's true negative. Let me just change the color. How do I? Oops. So let me use this one. So the first situation is true positive is here because it's true and I return positive. Okay, now it's not infected and return negative. This is actually true negative, which means I give you the right prediction, right? I predicted negative events, but it's the right prediction. Now let's see the errors, right? A person is actually infected by COVID-19, but the test returned negative. What's that situation? Anybody? So what I predicted is negative. And is this prediction right or wrong? It's wrong. So that's called false negative. Make sense? So I predicted as negative, but I know this is a false prediction. So this is called false negative. Okay. And we call this one type 1 error. Let me see, let me confirm, is that type 1 error or not? Yes, that's sorry, that's type 2. We call this type 2 error. All right, now let's see another error. This person is not infected, but I predict this is positive. So I predict it to be positive, but this, once again, this is a wrong one. So this is what? This is false positive FP. And this is called what? Type 1 error. And this entire thing is called what? Confusion matrix. And we have these 2 types of error in machine learning. Make sense? You guys probably remember when you learn statistics, you have heard the word type 1 error, type 2 error. That's what they are. Type 1 error, type 2 error. Now, question. Which is more dangerous? Type 1 error or type 2 error? Anybody?
I'd say a false negative is more dangerous than a false positive.
False negative is more dangerous, right? So which
Yeah.
means in this case is type 2 error is more dangerous, right?
Mm-hmm.
Okay, yeah, great. For COVID-19 case, yes, this FN false negative or type 2 error is more dangerous because if we say this person is negative, but this person is actually infected, this person could infect more people, right? It depends, right? So let's say our model is to predict if this person is using hard hat correctly, then type 1 error, type 2 error, which one is more dangerous? In that case, type 1 error is more dangerous. Why? Because if the person is not using the hard hat, but I predict it to be using the hard hat, so I'm committing what? I'm actually committing a false positive error. Make sense? Where's my mouse? I'm actually committing this error. It's type 1 error. So for that case, type 1 error is more dangerous. So it totally depends. Okay. So now I have the sense type 1 error, type 2 error, and this confusion matrix is the basis for us to evaluate the performance of a model. How? Let's go to the next slide. We have 3 important indicators to show the performance of model. Accuracy is probably the most commonly one that you heard. We always say, oh, how about the accuracy? What about the accuracy of your model? But in fact, in machine learning, you know, if you talk to the computer science guys, they often use recall rate and precision. So this is the formula of them. I know this is very abstract, but let me try to do explain that in an intuitive way. We are doing the area size comparison. What are desired by us? What are the desired? Sorry, let me repeat that. What are the desired outcome we want for a machine learning model? We want this to be as big as possible. The true positive. So, for example, we want to predict something is happening. We want to predict a shooting event is happening based on the sound. We want to predict a person is doing something stupid based on the camera. So for machine learning, we want the positive, but we want the true positive. So we want to predict something, wow, something's happening, that's positive, right? And we want to be correct, which is true positive. So we want this area to be as big as possible. Now, we need to compare it with something, the basis to compare it. So one way we can compare it is this. Use this one divided by the entire size here. So use this box divided by the summation of this box. This is called precision. So it's kind of like we predict, you know, my model predict something is happening, then there's a chance that my prediction is correct and there's a chance my prediction is wrong. Let's say 90% of chance my prediction is correct, positive prediction is correct, and 10% of chance my positive prediction is wrong. Then my precision is what? 90% divided by 90% plus 10%. That's 90%. Make sense? So I use this one divided by this one. That's called precision. Make sense? So I'm predicting something, and the chance I'm correct. That's called precision. But we do have another even more popular erase everything indicator. So let me, how do I erase all ink? Okay. And this is something called a recall. So I'm using this one. Once again, I focus on this one. I want this one to be as big as possible. And now the base for my comparison is this size. Okay. So which means when something is actually happening, the likelihood that I can predict that successfully. So let's say when the shooting event is actually happening, the chance I predict that it can trigger my machine learning model. This is called a recall rate. So when something is really happening, the likelihood it will trigger my machine learning model. And finally, the accuracy is actually this one divided by the entire size. Make sense? Oh, sorry. This one plus this one. So the true positive plus the true negative, which means out of all the prediction, the likelihood that my prediction is correct doesn't matter if I'm predicting the positive things or negative things. My prediction is correct. Doesn't matter if I'm predicting you are infected by COVID-19 or you are not infected by COVID-19. The chance I'm doing the right prediction compared to all the predicted result, that's called accuracy. This is the most commonly used one, but this is actually the most popular for machine learning literature called recall rate. Okay, so once again, this is abstract, but let's use this example. Okay, let's say this Titanic just hit this iceberg, right? And we have 170 observations. Let's say 170 people. Okay, let's say that's 170 people. Some people are died, some people are survived. Okay, so this is the predicted, this is the actual. All right, now everybody, let's calculate this one. So let's identify true positive, true negative, false positive, and false negative. So which is true positive? Which means I predict a person is died and this person is actually died. Let's say the dying is the trigger event, is something we focus, right? Because it's important for me to know how many people died. So the true positive is this, right? You know, they actually die, and I predicted it to be die. So I'm predicting a positive, and my prediction is true. Make sense? Okay, so what is true negative? Anybody? Which number is true negative?
45.
Was that 45, right? So I predict person survived, mean not dying, and actually not dying, so 45. So what is a false positive? I predict to be die, but in fact, my prediction is wrong. Is what? Which number? 12, right? So I predict to be not, but in fact it's and a false negative. Oh, sorry, I was wrong. Should be 28. That's the false positive, correct? Make sense? You know, I predict to be died. I predict to be positive, but in fact, the person survived. You know, my prediction was wrong, so that's false positive. And finally, false negative should be 12. Make sense? Okay. So what is type 1, type 2 error? Type 2 error is false negative. Type 1 error is false positive. Okay. So now let's do the calculation. Precision. Let's use the formula. So maybe I think it's easier for me to maybe got this thing, put this in here, make it a little bit smaller. Okay, everybody, get your calculator and let me know what is the precision of this model. Precession is what? This number compared with this number. Anybody?
0.89.
Oh, what number divided by? Can you show us the numbers?
And 94 and divided by 106.
So 94 divided by what? The summation of what numbers?
106.
So divided by 94 plus 12. Anybody
No,
else?
not 94 divided by 94 plus 12.
Do you guys agree?
94 divided by 106.
Okay. Do you guys agree?
94 plus 45.
No.
94 divided by 94 plus 28.
Exactly. So because
Okay.
we rotated a matrix. Get the point? So this is, false positive. Here we focus on the positive prediction. Here I all predict that, but 28 of them are wrong prediction. Make sense? So let me repeat again. Precision means I focus on my prediction and I want to check how much of my positive predictions are wrong. Let's say I focus on predicting how many people are died. So this is my prediction. Actually, I predict how many people are died. 122 people are died. That's my prediction. Make sense? But out of the 122, only 94 actually died. 28 survived. So the precision of my prediction should be, I'm right in terms of the 94, but I predicted 122. So this is my precision. Make sense? You understand that, Junyi?
Yes, I got it.
Okay, now let's see recall rate. What is recall rate, guys? Recall rate is what the Junyi said, right? So for recall rate is we focus on this event. We want to know if somebody's died. And how many people are actually died? '94 plus 12, so that's 106 people actually died in this disaster, right? And how many times my model can capture that? I know 106 people died, but how my model didn't capture all 106. My model only captured how many? 94 of them out of 106. So what's that number?
.89.
So it's 0.89. And what is the first number?
0.77.
Okay, now you see the recall rate is very different than the precision. Make sense? Now let's calculate accuracy. So for accuracy, I don't have a focus. I don't care if people died or survived. I just care if my model is good or not. Then what's the accuracy calculation? What is the right calculation prediction have? 94. That's correct prediction, right? Plus, what is the other correct prediction have?
45, which is
45.
predicted survive and actual survived.
Yes, divided by the total number. I have the total number already. It's the summation of the four numbers, right? 179. So then what is the rate? What is the accuracy for my model? Anybody got the calculator?
0.776.
0.7. All right. So here's the limitation of the accuracy. Here's the limitation of the accuracy indicator. You know, we think our model is only this much accurate, 0.776. But if my focus is to predict the dice of people, that's the function I desire for my machine learning model, which means what? My model did pretty bad in this way. This is why my accuracy is not that good. But my model is pretty good in terms of calling if this person's really died. So my recall rate is higher than my accuracy, right? So in this way, my model is functioning to serve the purpose of predicting what? Dies. Make sense? So this is why recall rate is more important for machine learning. Because what? Machine learning has a purpose. It's very difficult to write with these months. Shoot. Machine learning has a purpose. Make sense? Now let me repeat again. Accuracy indicator is just a neutral indicator to show the goodness of model. But if we want to evaluate the model can serve certain purpose, certain function, like in this case, I just want to predict the death. That's my purpose. So how do I evaluate the goodness of my model just serving this very specific purpose? That's called recall rate. Make sense? And the precision is, you know, for this particular purpose, the accuracy of my prediction. That's called precision. So precision and the recall rate are all purpose-driven, and the accuracy is a more neutral indicator. Make sense? Sorry, guys, I have to take a phone call. Let's take a 10-minute break. Let's return at 5:45. All right.